All right, so what we have here is an ideal gas law problem. And the ideal gas law states that P times V equals N times R times T. And sometimes you might not be sure if this is an ideal gas law problem or a combined gas law problem. But one major way to find the difference is in an ideal gas law problem, you usually have one of each variable. In a combined gas law problem, you have two pressures, two temperatures, whatever. So let's go to the problem and identify every value given. So the first value is 10 liters. So liters is a unit of volume, so I'm going to write V equals 10.0 liters. It says at a temperature of 24 degrees Celsius, so T equals 24 degrees Celsius, and a pressure of 300 kilopascals. So I'm going to write all of those things down. And it says how many moles are in the container. So moles has an abbreviation of N. It's not M because M is mass. We don't know that, so I'm going to write question mark. You might say, okay, well, P, V, N, and T, R is the only one not accounted for. But R is a constant. It doesn't change. It's 0.0821 liters times atmospheres over moles times Kelvin. This is something that you'll be able to look up. You'll probably have it memorized after doing enough of these problems, though. So this is a value like pi. It doesn't change. It is something that is constant for any ideal gas. So we're looking for n. So this is really just an algebra problem. The one catch before we do it is you need to make sure that everything is in the proper units. So if you look at the units of R, every other unit must match that. So in other words, volume is in liters, and that's okay because liters is in R. Temperature is in Celsius, though, and that doesn't work because the units of R are in Kelvin. So we must convert Celsius to Kelvin. And to do that, when you go from Celsius to Kelvin, you must add 273. So 24 plus 273, we're just going to add that up. It's going to give us 297. So that's our new temperature. That is the temperature you use in the ideal gas law. You cannot use this. Pressure is in kilopascals. That must be in atmospheres. kPa won't work, so we just need to know the exchange rate between those. It's 101.3 kPa equals 1 atmosphere. So we'll do a quick fence post. 101.3 kPa on the bottom because we want to cancel. 1 atmosphere on top. And you should know it's going to be about 3 atmospheres because if 100 kPa is 1 atmosphere, then it's going to be awfully close to 3. Dividing by 101.3, I get 2.96. All right, so that's the first thing. Make sure all your units match properly. Now it's just a matter of solving for n. So if PV equals n times r times t, to get n by itself, we're going to have to divide both sides by r times t. Because when we do this, the r and the t cancel on this side, giving us that n equals p times v over r times t. And now it's really just a matter of plugging in the numbers. So n equals, we're going to do 2.96 atmospheres times the volume of 10.0 liters divided by 0.0821 liter atmospheres over mole Kelvin times the temperature of 297 Kelvin. So I'm going to divide those all. So 2.96 times 10. It's going to give me 29.6 on top. And then on bottom, 0.0821 times 297. It's going to give me 24.38. I'm just going to divide those. And then we get n equals 1.21 moles. So that should be my final answer, but it never hurts to check. We know the original equation, the ideal gas law, was that PV equals n times r times t. So to check this, we can just do a quick check and see what is P times V. So P, we said, was 2.96 atmospheres, and V was 10 liters. So 2.96 times 10 is 29.6. Does that equal n times r times t? So 1.21 times 0.0821 times 297. So multiply that out, 1.21 times 0.0821 times 297. I'm getting 29.5. So I know there's always rounding issues, so this is pretty close. So we probably did this correctly. So there are 1.21 moles of gas in this container. And you can do this type of problem solving for any of the variables, P, V, and R, T, as long as you're making sure your units match those found in R. If they don't match, you will not get the correct answer. So, until next time, I am Derek Genova. Have a delightful day.